In this case, we need to use mathematical induction to prove that 2 plus 4 plus 6 plus 8 up to 2n, that is the sum of the even numbers, is equal to n squared plus n, for n in the positive integers. So we start with step 1, which is the base case, which in this case is when n is equal to 1. The left-hand side is equal to 2 times 1, which is equal to 2. The right-hand side is equal to 1 squared plus 1, which is equal to 2. What that means is when n is equal to 1, these two are true, these two are the same. So that means the statement is true when n is equal to 1. Now let's look at step 2. Step 2 is when n is equal to k. And we're going to assume that 2 plus 4 plus 6 plus all the way up to 2n, sorry, not 2n, 2k, is equal to k squared plus k. That's our assumption. Step 3 is when n is equal to k plus 1. And let's first of all think about what I want to show. What I want to show is that 2 plus 4 plus 6 plus 2k plus the next number, the next even number, which is 2k plus 1, is equal to k plus 1 squared plus k plus 1. Let's start with the left-hand side. The left-hand side is equal to 2 plus 4 plus 6 up to 2k plus 2k plus 2, expanding that little bracket there. And this is equal to the assumption step. So we're going to replace it and make in the substitution for k squared plus k. So we're going to replace all that pink bit with k squared plus k. And we still have here plus 2k plus 2. This is equal to k squared plus k plus 1 plus, actually I'm going to make it plus 2k plus 1 plus k plus 1. So I've still got the same number of k's, I've still got 3k, I've still got the same number of numbers, I've still got 2. Now the reason I wrote it like this is because I know what I'm aiming for. I know I want a k plus 1 at the end. So I'm going to separate that k plus 1 at the end. And to separate that k plus 1 at the end, that means I have k squared plus 2k plus 1 to start with. K squared plus 2k plus 1 factorizes to k plus 1 squared. And this is k plus 1 at the end. And I can see that that is what I had on the right-hand side in my want to show. So that is exactly what I wanted to show. So now I've shown that the k plus 1 term is also true. Finally, step 4, my conclusion, and I'm going to cheat a little bit here because I'm going to paste in the same conclusion that I used in the previous ones. You would obviously have to write this out by hand. That hence, by the principle of mathematical induction, since a statement is true for n equals 1, and if it is true for n equals k, it is also true for n equals k plus 1, it holds for all values of n, where n is a positive integer.